Good morning, everyone. So, let me just make a couple of announcements. As you know, today we have PWS in IMSA lecture by Jackie Mesquita, and that is going to be at 5:45 this afternoon. There will be refreshments after that. So this is a new initiative that we initiate in IMSA in collaboration with PWS. And a little bit more detailed plan for the lecture's celebration will be put it on the website later today. So, all right, so let's continue with our morning session. So,
I'll introduce you.
that's okay, it's okay.
So it is a pleasure to introduce our director, Arisa, that has been doing so much for it's very difficult. Projects and collaboration networks of the company. And also, in certain implementation, he'll be speaking about this very exciting. Universal invariance.
Thank you, Ernesto. So, it was Max who was supposed to do this talk, but he couldn't make it. And I will give a very general explanation of where all this is coming from, and more precise definitions will come in the next talk by Tony Pantes, and the Equilibrium part will be explained on Thursday by Leonardo Gavinaghi. So, and just since we have a rather broad audience, let me remind you that variational geometry asks the question, let's say we are over the complex numbers, when the few operational functions of objective variety is morphed to the two operational functions of an independent variable where n is the dimension of x. And this is a very classical question in algebraic geometry, parallel to the questions in topology when manifolds are morphed to sphere. And so the classical example of the conic goes back to, let's say, Archimedes, who knew how to prove that the conic is variational to the line, since there is a one-to-one map coming from a projection from a point on the conic, and that actually works in any dimensions for any quadratic over the complex numbers. So if you change the field of definition, you can ask similar questions, and of course the answer is different. And so one of the goals of my talk will be to emphasize how these methods related to mirror symmetry and conformal field theory actually allow you to look at this change of fields from this perspective as well. In fact, we'll be only scratching the surface here. So this parallel theory with quantum input models or required with geometric stability conditions will allow to see even more on the level of singularity theory about the minimal model program associated with the funnels that we get in mind. So in particular, the piece of links and higher links can be explained from the perspective of funnel input model. So, so that's why I'm going to try to explain where all this is coming from, so that people try to explore further application. So now let's return to the cubics, which will be the main subject of our discussion. So if we have a smooth cubic curve in V2, so it is known due to Riemann that this cubic is not rational since it has a fundamental group. And in the case of the two-dimensional cubic, it was known to Del in the middle of the 19th century that this is for P2 in 6 points in general conditions. And of course, if you change the field over which this two-dimensional cubic is defined, that is no longer the case, and we'll return to this observation in a while. Now, the next cubic is the three-dimensional smooth cubic in P4, and so there are also people in this room that know much more than I do on this subject. So it was proven by Clemens and Griffiths that such smooth cubics are not rational, and the invariant that was used there was intermediate Jacobian. In fact, to be more precise, is the delta divisor of this intermediate Jacobian, which happen to have singularities of two big co-dimension 5 in this case, and Jacobians of Riemann surfaces would only have delta divisors of Jacobian of Riemann surfaces would have co-dimension of their singularities in dimension, co-dimension 4. So now, of course, the main observation is that if you blow up a three-dimensional funnel, the only contribution that homology would appear there, the homology of degree 3, only the third homology change, and the thing that you are running by blowing up curves is essential part that counts actually is the Jacobian. Of course, blowing up point is another story. Will not get much out of it. So now let's briefly remind you that the Hodge diamond of the two-dimensional smooth cubic looks in the following form. We have 4 algebraic cycles in degree 0, 2, 4, and 6. And then transcendental 5 and 5. So in the middle we have Hodge diamond, which looks very much like the Hodge diamond with a genus 5 curve. And as I mentioned, a deeper exploration of the Meyer theory, in this case, allowed Clemens and Griffiths to show that this is not coming from a genus 5 curve. The different animals, so this is why three-dimensional smooth cubic is not rational. So now, so this is something that I already worked with you. And there are many ways in which you can explore to study rationality questions. So, I mean, I'm certain that I have missed some of them. So, we already mentioned the method of intermediate Jacobian. So, approximately at the same time, Artin and Mumford example of only bundle was introduced where the Trojan homology was used as a variational invariant. So there are for geometric methods, and this is the method of variational homomorphisms introduced by Stolsky and Marin, which they have applied to the case of three-dimensional party. And of course, very powerful regeneration methods actually originated by Clemens a long time ago, but very successfully applied to by Moizan and Powers to the case of third-dimensional funnels. So they degenerate to funnel which has not so essential singularities, usually ordinary double points, and then that leads to the creation of a non-trivial Brouwer group, which amounts to non-triviality of Chow zero, but Chow zero behaves well in families, so therefore the initial manifold we can start this with is going to get non-trivial Chow zero, and that's how many examples were shown to be not rational. And of course, there are analytic methods, the method of multiplier ideal shifts, but so some of these methods are going to be discussed today in our talk on parallels to this method. Now, of course, as I mentioned, these methods don't apply to the funnel manifold that we want to explore, and you'll be hearing about today. Now, the four-dimensional cubic, generic one, and so we don't have intermediate Jacobian in this case, and the method of degeneration doesn't work for cubic, for any cubics, because I mean, if you degenerate a cubic and you produce one singular point, it's rather clear by the same method of Archimedes, if you project from this singular point, the line is going to intersect the cubic just in one more point, and that gives you one-to-one map with Cn of the corresponding dimension. So the singular cubic of any dimension becomes rational. So
Wait, is this question independent of which cubic you choose?
for generic, yeah. So I don't know if Tony will have time to explain a different argument for the cubic with the plane. So if there is a difference, you need to enhance the atom theory in order to. So, but this is only for generic. And the idea that I propose here is to use some notion of homological mirror symmetry. Now, of course, I'll just try to indicate where these ideas come from, and then at the end of we're actually going to try to forget about homological mirror symmetry, and the way to avoid this is to take the information that comes from the A side of mirror symmetry of symplectic manifolds and combine it together with the algebraic geometric theory that we know that on our funnel, and then this new type of core structure, which we call atoms, is going to serve as an abstraction to rationality. So let me briefly remind you what homological mirror symmetries, and now homological mirror symmetry suggests applications to A side to questions related to variational geometry. So the homological mirror symmetry is about equivalence of two categories. So we rather add here. So one of them is category of coherent shifts over smooth projective variety, which are our funnels. And then the other is category associated with the open symplectic manifold Y and function unit W. So now to both sides of this mirror symmetry, to the B side, which is our funnel, we associate the category, which is the derived category of coherent shifts. And then to the A side, we associate a category associated with the singularities, this vibration. So now the vibration that I described here has made clear the denominator. You are going to see that this is just a family of open elliptic curves. So if you clear the denominator of this function, you see that this is a polynomial degree 3 that you're getting. And of course, I'm oversimplifying here because there is a parameter. In this case, it's just one parametric familiar potential. P2 is equal to Z. But in general, there are parameters that participate in this orthogonal models. And now, the main observation that made me start thinking, about behavior of orthogonal models under variational transformations is the following. So, if you blow up a point on P2, so the host diamond that changes by just adding one additional algebraic cycle. So from 1, 1, 1, we go to 1, 2, 1. The corresponding category changes by us adding just one exceptional object. But the effect that this ball has on the Landau input model is that we actually create one additional singular fiber. And so there are a category which changes by adding one exceptional object. So its counterpart, a new singular fiber and additional vanishing cycle, which is called Blanchard symbol. And this Blanchard symbol is responsible to the exceptional object to extending the equivalence with the category of different shifts. And on the A side, we have one more singularity, one more symbol, and that's what make correspondent mirror state tall. So that's it has been always the intriguing part for me. And so I learned about this Landau construction from Buffer was in Caltech approximately in 2003, and then from Michael Douglas and mainly from Kapustin. And so then in 2005, I was organizing this Woodstock algebraic geometry, and so I heard a talk by Joe Paris about the work of Kassett from four-dimensional cubic. And so at that time, I started playing with the Landau visible model, and I started realizing that indeed it exists quite a bit about variational geometry, and I'll try to emphasize this to you in that explanation. So of course, it took quite a bit of time, but this is a little bit like a well-founded knowledge. So in fact, I think some philosopher from Florence gave an example what well-founded knowledge is. So you walk in the desert and you believe that there's a oasis. And so you walk, and you get to the oasis. In fact, there's nothing there. But if you actually dig deep enough, there is a water in this place. So you were correct. And in my case is that if you have an excavator named Simkonsevich, you can find water even if there isn't one there. So, and indeed, eventually, Max joined the project, and so basically taught me how to avoid all these difficulties coming from so-called quantum categories, which indeed abstraction. And then I needed to add some apostles, Max, Tony, Leonardo, Rino, all with Latin, not with Jewish names, in order to make clear this approach to the world. So the question that is we have in our mind here is how to really record this data coming from the Landau-Ginzburg model to create a theory, but avoid any use of mirror symmetry. And let me demonstrate one more example, and that is the example of that we have already looked very carefully on the this side, the example of the three-dimensional cube. So I give you one Landau-Ginzburg model given by this function W on C3. Now there are parameters that I can measure. In this case, there are 4 parameters. It's the number of the algebraic cycles is 4, and algebraic cycle 4 4-dimensional space. And so now, if you look at this Landau-Ginzburg model and you analyze it, so you see that it is a vibration of open K-T surfaces, and 3 of these fibers are singular. 2 of them have just ordinary double points as singularities, and 1 is open configuration of 3 rational surfaces, and 3 others intersected in the perpendicular direction. So now, I mean, I was always interested to know how much of the geometry of the initial cubic does this Landau-Ginzburg model see. And one thing that you can compute is the homology of the perversive of vanishing cycles, and associated with this family of K-T surfaces. And if you compute this, you see that basically the Hyper's homology recover the course diameter of your initial cubic, which was 5, 1, 1, 1, 1, 5. And so the first, this is basically the data that you get from the course diameter of the three-dimensional cubic, but rotated by 90 degrees. So the perversity of vanishing cycles, meaning the fixed singularity theory, tells you quite a bit about the core structure of your initial manifold. In fact, more is true. So you could look deeper and study the monogamy of this operation of surfaces. So let's call with ZT the generic fiber of compactified family of these surfaces. And let's call by mu the monogamy of acting on H2 at this very singular fiber. So now you can compute this monogamy in this case due to the fact that the curve of three-dimensional cubic is C. This monogamy is going to be given by a 3 by 3 matrix, and in this case, that is a matrix with one epsilon square, where epsilon cube is equal to 1. Okay. And in fact, more generic statement is correct. That if you have just giving you one direction of the statement, if you give a power triple with pk equal to z, then let's say it's not equal to degree, then this power is rational if and only if the monogamy given upstairs is nilpotent, and we get only once on there. Now this is rather dumb statement, and the way it is proven is you know the rational power triples from Stolsky list, and you know the corresponding bundle of input models, and you just compare and come to this statement. So it has been a big interest to me to find out if what is the conceptual explanation of this path. But and so I'll try to give an answer to this question towards the end of this exposition. So now
What is the definition of a monodromy operator being no closeness?
I mean, if in this particular case, if you have one on there, no roots of unity. So by this I mean it is actually called strictly uniform. So the better statement is that I wasn't very careful that they are rational if and only if the corresponding modeling gets lost from there. So now what we want to do is to combine both sides of mirror symmetry and this side to create a new type of structure which will lead to birational invariance, and that's what I'll be trying to explain going forward. So the idea for this again comes from the example of three-dimensional cubic. So we have the following splitting of the whole diamond. So we have 3 pieces. In this particular case, 2 are this 1 and 1 corresponding to H0 and H6. And then this big piece, which looks like the whole diamond of the Genus-5 curve, is the 3rd piece of this splitting, and the splitting actually comes from the splitting of this. Splitting comes from different singular fibers in the corresponding bundle with input model. corresponding part of this book model. So we have splitting of these three pieces of the whole diamond, and each of these pieces corresponds to different singular fibers. So now the singular fibers and the critical value of this Landau-Windburg models actually in mirror symmetry correspond to the eigenvalues of the operator of the quantum multiplication by C1 px, and that's the starting point of avoiding any connection with mirror symmetry. So instead of talking about Landau-Windburg model, so we'll do the following. So we take our funnel and we think of it as a bright variety with its Dirac homology, and then so we think of it as a symplectic manifold with the corresponding symplectic form coming from the Fubini-Study metric on in PN where this funnel manifold here is embedded. So now it does have classical quantum multiplication. It does have classical symplectic Rom-Whitman theory associated with it as a symplectic manifold, and this Rom-Whitman theory is recorded by the solutions of this quantum differential equation. So ddu plus 1 over u squared k plus 1 over g, where k is the operator of the quantum multiplication by C1 of x, and then g is just some grading operator. So the solution of this quantum differential equation is the one function, the extensions of which produce the notorious Rom-Whitman equation. So we start with x, our algebraic variety, but we enhance it with this additional structure coming from the quantum multiplication on this symplectic manifold with symplectic form coming from the Fubini-Study metric. And the theorem that I want to formulate, and so you will hear a little bit more about it in next talk, is that actually, so this eigenvalues of the quantum multiplication of by k gives us a splitting of our homology, the homology of our initial funnel x into elementary pieces, and then the statement, which will be explained in more details in the next talk, is that this splitting of these elementary pieces is bidirectional invariant, modulo, of course, the contribution of subvariety and collimation to that, and of course, adaptation of the symmetric group. So this splitting that we were seeing from the Landau-Windburg model now is the splitting of the homology coming from the eigenvalues of the quantum multiplication by k. And of course, as I just mentioned, you can actually enhance this splitting by putting additional structure associated with this structure, so on and so on. Maybe that will be discussed in the next talk. So now, here's a general picture that one can apply to this situation. So it's a certain spectral covering over the space of all algebraic structures, algebraic cycles that we could associate with this funnel. So the operator EFU, it's an Euler field given by the formula C1 of TFX plus the sum of some coefficient times parameters which Ti, which parameterize the model, which parameterize the space of all algebraic cycles, and delta I are bases in this algebraic cycle. Now, for different Di's, so we have different eigenvalues on the operator of the function multiplication by k, and this gives us a spectral coloring of associated to this Euler field over all algebraic cycles. Now, of course, there is a multiplication divisor, and as we are going to see very soon, it plays an important role if we study equivariance questions. But the atoms are actually the components of this spectral coloring at generic point. For generic point of this spectral coloring, we have this color, generic splitting, and the atoms who correspond to this splitting. So an important example that is going to play a role is that if we have smooth projective variety X, which is with K of L to M, then the atom consists only of one point, and so that is going to be the building block of all of our considerations. So now, if this splitting is a bidirectional invariant, so I would like to briefly discuss how this can be applied to different cases. So let's go back to the case of three-dimensional cubic. So we get this splitting, and according to the theorem that I have mentioned, so this splitting is a bidirectional invariant. Of course, as I said, modular contributions are so varied as all dimension 2 and I. And all we need to worry about is what is happening with this piece H corresponding to coarse diamond that looks very much like the coarse diamond of genus 530. So now all we need to notice here is that the self-functor acting on the homology in this case acts like the self-functor PS, S in power 3 is equal to shift by 5, and that's not how the self-functor of Riemann surfaces do act on their homologies. So you conclude that this piece cannot come from a Riemann surface, and therefore this three-dimensional cubic, multi-dimensional cubic is not rational. In fact, since we do know what self-functors are in case of many other follows, we conclude that for all of them, that we give this rationality or precise non-rationality construction, and so exactly this monodromy that I had mentioned is in the statement of Joukowski can be explained with the fact that we have some self-functor which is form of a rational number. In this case, it's 5/3. And now, of course, that's a very easy application of this splitting theorem. So as we are going to see in the next lectures, this becomes a little bit more involved in higher dimensional example. So now, what I would like to discuss is a certain enhancement of this theory of atoms, this time based a little bit more on something which is called conformal fluid theory. So now, in the 80s, two parallel schools developed theories of singularity and conformal fluid theory. And these theories were developed in the same city, but the groups developing this theory didn't know about it. each other. Maybe they did, but didn't make a connection. So one group, this was the group of Krishnik and Homological. So they were developing this theory of central charges. And the other group was the enormous group with many of whom I was familiar, of Arnold's. And so they were doing something which was later called spin spectrum associated with this variety. So now, in fact, there was a conjecture at that time, proven later by Spindler, which was called semi-continuity conjecture of the spectrum. And physicists actually did have a statement that was connected with it, and that was called the homological C theorem. Exactly that if you move from the modular space of conformal field theories, the first central charge only can go down dimension. Your behavior is true for the numbers of the spectrum. So now it was Buffer actually who made a connection between these two, and he actually added additional component, the asymptotics of certain differential equation. So it's a beautiful paper, and of course Buffer could care less about homogeneity, that I can assure you. But, so in a beautiful paper, he made a connection between asymptotics of the certain differential equations, very simple AD singularities, and conformal theory associated with them. So this is the picture that was more or less explained. That's special of it in Vapacheko's paper, but he was aware of the fact that semi-continuity of spectrum is related to the homological situation. Now, of course, and after the work of homological, McCoy, and many of these people, I mean, so a lot is known about the behavior of other central charges, about their dynamics, if you move in the modular spaces of conformal field theory. And all this can be explored to derive other variation effects. We're just scratching the surface here. And so now let's indeed make use of the class of these numbers, and that is the so-called central charge in the conformal field theory. So now I'll only be talking about the asymptotics of the sub-exponential growth solution of the quantum differential equation, which I have formulated there. And so let's say that it's a little bit of a lie, but I can explain this after the lecture. So let's call the delta the biggest asymptotic. And now, so the theorem is that if this delta, which actually in the case of quantum hypersurface can be computed as dimension of x minus 2 times n minus d over d. If this number is bigger than dimension of x minus 2, then x is not rational. And so one can easily compute that in the case of three-dimensional cubic. So the big N is 4 and D is 3, so we do have 5/3, and we get that three-dimensional cubic is rational. So it's not rational. And I give two other examples of other functions of higher dimensions, which are proven to be not rational by the application of this new non-rationality criteria. So the way the proof is done is basically you need to restrict yourself to this atom associated with the biggest piece of the decomposition that I have mentioned. So in the case of three-dimensional cubic, this is 1551. and restrict your differential equation only on this piece. The asymptotics come naturally, of course, they are distributed to modeling, and that's how you actually conclude the operation and because they come from the splitting, and after that you just need to compute that they are bigger than the dimension of x minus 2, and you do compute this in the boundary of this modular space of homogeneity or of the singularity, and then you need to use some continue the statement that if you go inside of this modular space, these numbers only can go down, so you're in business. So in any case, the mirror symmetry statement that is hidden behind all this discussion is that so if you have one Ginsburg model, it has singularities, and these singularities have Stimbring spectrum. So this Stimbring spectrum, classical notion in the theory of singularity, is actually related to the asymptotics of the quantum differential equation. That's the symmetry statement behind all this. So this is another simple numerical abstraction that comes from combination of mirror symmetry in the form of utility. So now let's play a little bit with very classical mathematics, which I learned from Yuri Ivanovich Marin, and not very successful for me exam, I must say. So, so at that time we were learning about non-rationality of different surfaces over different fields, not over the complex numbers. So as I mentioned to you, the cubic surface over the complex numbers is rational because it's flow of P2 in 6 points. But if you change, so it's not Z2, but can mistake, means that the regard of this two-dimensional cubic over the field K is Z plus Z a second. So if you change the field from the complex numbers to some other field such that this cubic has regard equal to Z2 in Z plus Z, then that cubic, as Mani shows in his paper in publication the Ashes from 6 years ago, is that actually such a cubic over this different from the complex number field is not going to be rational, and so he introduces the notorious these days criteria, which is 2K C plus S, which, if I'm not mistaken, still is not completely proven that is giving you a criteria for rationality of calling bundles, but in dimension 3. But in dimension 2, this is what Marin computes in this classical paper. So if the PKR is equal to Z plus Z, then this cubic has a structure of a conic bundle. And you can compute the number of the singular fibers of this conic bundle by Noether's formula. So we have 8 minus degree of this cubic, so it's 5. And then we compute this quantity, the linear system, 2K Q1 plus, by this case, it's S, the discriminant loci of this conic bundle. But in this particular case, as we computed, is 5 points. And so this linear system, 2 times the canonical plus of the base, in this case Q1, plus 5 points, but discriminant loci is not empty. So you conclude that by Marin approach, this is not rational. So Marin's criteria in this case is that over this field, the two-dimensional cubic is not rational if and only this linear system over the base is not empty. So in this case, we have -4 + 5 is certainly not empty. So now this is how we can put that two-dimensional cubic over this field if not rational. Let's try to look at this from the perspective of the Landau-Ginzburg model. So if we consider the cubic over the complex numbers, so the number of algebraic cycles over this cubic is 9-dimensional. H0 + H4, that's 2. And then we have 7-dimensional figure over the complex numbers. So we have 9 algebraic cycles over this two-dimensional cubic. And so if you consider the corresponding Landau-Ginzburg model, initially it has two singular fibers. One is a very singular, it's a E6 singularity plus one other singular fiber. But because we have a huge space deformation of this singularity, and you have a lot of parameters, this is your algebraic cycles, so you can deform your Landau-Ginzburg model in a way that you actually only obtain ordinary double points of singularity. And so if you compute the strip spectrum for an ordinary double point, it's just trivial. But if you restrict the parameter space, in other words, if you deform only over this Z2, you cannot split the singularity from E6 tilde to ordinary double points. And if you compute the cubic spectrum from this E6 tilde singularity, in this case, it is going to be 5, 6. Certainly, it's bigger than the dimension of 2 minus 2, dimension of x minus 2, which in this case is 0 for surfaces. So that's how you conclude with the application of this Stippling spectrum type of invariance that over this field, this two-dimensional cubic is not rational, which is not new, but it's a different way to think about it, which suggests that the theory of atoms can be used to study not only rationality questions, but questions about G non-rationality. In other words, you have a group acting on your manifold, and then you consider all the bilateral transformations which are equivalent with respect to this group, and you ask if this funnel, let's say it's can is G rational or not. Now you'll hear more about this on Thursday, but let me just do one example, which I learned in 1984 from Miskowski, and that is the hypersurface of degree 1, 1, 1, 1 in Q1 to the 4. So this is a nice funnel manifold, which is obviously rational over the complex numbers, since it's nothing else but just plot of Q1 plus Q1 plus Q1 in an elliptic curve. So now, if you think about the atomic structure of this funnel over the complex numbers, it is going to consist of 8 pieces. Sorry, I apologize, 9 pieces. 1 of them correspond. I'm sorry, 8 of them correspond to the homology of Q1 plus Q1 plus Q1. There are 8 of them, and then 1 is to this elliptic curve. But now, if you restrict yourself to only equivariant algebraic cycles, so using the action of Z4 acting transitively on this Q1s, then that restricts significantly the space of deformations, and you have fewer atoms. In fact, you have only 3 of them, and definitely the biggest one, doesn't look as an atom that could be coming from a Riemann surface. In fact, it looks like 1, 2, 3, 1. That is not the first diamond of a Riemann surface. So that's how you can put that over this let's say, fields, the R group which suggests on Z4, or if you like, if you just study equivariant non-rationality with respect to the group Z4, this Z equivariant, Z4 equivariant threefold is not Z4 rational. So some partial cases with additional data were known before that to Kuznetsov and Prokhorov, but this is clearly a new Z4 equivariant non-rationality result in this particular case for all of them. So after the work of Chinkel and Chotov, this has been a very popular subject these days, and after the work of Pestun, Puntsevich, and Chinkel, but you'll hear more about this, I believe, from Thursday in Leonardo's talk. I'll stop here. Thank you very much.